Consider a JavaScript snippet that fires a synchronous log, a timeout with a 0-millisecond delay, and a resolved promise. Upon execution, the promise logs to the console first, appearing to jump ahead of a timeout that was scheduled with no delay. This behavior reveals whether a developer understands the underlying mechanics of the JavaScript engine or is simply relying on trial and error. We are going to deconstruct the JavaScript runtime engine to expose exactly how it sorts and prioritizes asynchronous operations. We'll decode the promise state machine, trace the immutable data pipeline, and analyze parallel concurrency combinators. Mastering this execution order allows developers to predict code behavior in complex, high-concurrency environments, where eventually isn't a precise enough timeline. A promise is a stateful object that represents the eventual result of an asynchronous computation. It is not a synchronous wrapper for a callback function. The event loop monitors the call stack and two waiting lines, the macrotask queue for timeouts and a higher priority microtask queue for promises. The engine completely drains the microtask queue first. Even with a 0 delay, timeouts wait until every promise executes. Internally, a promise operates as a strict one-way state machine. It always begins in a pending state. The JavaScript engine continues executing synchronous code on the call stack, while the asynchronous network request processes in the background. From there, the object transitions to fulfilled if it succeeds, or rejected if it fails. Developers frequently confuse resolved with fulfilled. A promise is resolved when it is permanently locked on to the fate of another promise, removing direct control. It is only fulfilled when it possesses the final returned value. Once a promise reaches either fulfillment or rejection, we say it has settled. At that exact moment, its state and its associated value becomes completely immutable. If you construct a custom promise but fail to invoke the internal resolve or reject functions, the object stays pending indefinitely. The associated callbacks never run, creating a silent memory leak. With traditional callbacks, you are often left guessing if an operation fired twice, failed silently, or never executed at all. A stateful object guarantees a single transition that external modules can rely on. To access the data inside a settled promise, we use three instance methods: .then, .catch, and .finally. Calling one of these methods does not mutate the original promise. Instead, the method immediately generates and returns a brand new promise object. Because each method returns a new object, we construct an immutable pipeline where one stage's return value becomes the next input. Watch how the parsed JSON body moves down the pipeline, fulfilling intermediate promises until it delivers data to the final callback. If a network error occurs, the rejection simply skips over every .then block in the sequence. It trickles down the chain until it hits .catch. You can then close the pipeline using .finally. This method executes regardless of whether the chain fulfilled or rejected, providing a reliable place to close database connections or clear interface loaders. Constructing these chains, however, exposes the application to a subtle syntax bug when developers mix ES6 arrow functions with promise pipelines. This excerpt highlights a common error: adding curly braces inside a .catch block without an explicit return keyword. This disables the implicit return. The block outputs undefined, which becomes the next stage's input. The engine throws no error, but the required data simply vanishes. Senior developers prevent this by treating the pipeline strictly as a series of inputs and outputs, deliberately managing the exact return value of every single node. Treating the chain as a strict series of isolated, immutable objects makes complex error propagation and asynchronous data flow completely predictable. Sequential pipelines process dependent steps, but complex systems routinely need to execute multiple independent operations in parallel. For example, a complex analytics dashboard needs to fetch user data, recent transactions, notifications, and weather metrics simultaneously. Wrapping these requests in Promise.all creates a strict dependency. The engine will shatter the entire batch and reject the operation if even one request times out. Promise.allSettled provides a fault-tolerant alternative. It waits for every process to finish and returns an array cataloging every individual outcome. The dashboard can render the successful modules and gracefully degrade the widgets that failed. When speed is the only metric, Promise.race settles the exact moment the first operation finishes, regardless of success. Conversely, Promise.any hunts for the first successful fulfillment. If the primary node fails, the system ignores the rejection and locks on to a secondary node. Promise.any will only throw an error if every single promise passed into the array fails, combining them into a unified aggregate error. These 4 static combinators serve as the primitive mechanisms for coordinating highly concurrent tasks. Selecting the correct combinator dictates the system's failure tolerance and resilience when fetching multiple resources. Promises are strict, stateful objects that the JavaScript engine prioritizes over standard callbacks by routing them directly through the microtask queue. Instance methods yield brand new objects at every step, creating an immutable pipeline that handles sequential data transformations and isolates errors. When operations must scale horizontally, static combinators allow you to dictate the exact concurrency rules of the overall system. To verify your understanding, open an editor and write a custom polyfill for Promise.allSettled from scratch, relying only on basic arrays and instance methods. Treating promises as a stateful data structure provides the foundation for building predictable, asynchronous logic that handles failures without cascading errors.